EX125. So I'm going to talk about homological algebra, and in this video I'm going to talk about diagrams, cone over a diagram, limits, colimits, intuitively as a limit of a cone, and then talk about functor that reflects limits and colimits. And in the next video, maybe I will talk about, I'll prove the fact that two arbitrary two limits commute. So let's recall. So you will find this recalling sometimes very intuitively, but not that formal. But the proof would be rigorous. Let me try. Yeah. So definition. Firstly, let me recall what is diagram. So this is not something I'm used to, but I will put some link a web page where those things are discussed. This is an intuitive way to think about something we're very familiar with. So I'm going to define it very informally. Informally, a diagram, a category. So intuitively, a diagram is the diagram, commutative diagram. For example, we know it could be a triangle, square, cube, or the more complicated shapes. And we will actually very intuitively to think of this as just a functor. A diagram in a category C is or consists of some objects of C connected by some morphism. So just think of example. Let's say you have some category. Let's say you have objects A, B, C, and some morphisms like this. Well, I'm saying that you could think of this as a functor from this category to this category, a functor. Right. And what I'm seeing that, so this is a diagram, and this is the functor. And obviously there is one correspondence, which I mean for other types of diagrams. You could think of there are different diagrams, for example, diagram like this is the diagram, and then diagrams like this, and then this is also gives you a functor. Diagrams like this gives you a functor. Let me do it in this way. Okay, and other examples and the colimit. You could think of this, what I'm saying is that a functor of certain shape, right? Or diagram of certain shape. This is like the shape of this diagram. Okay, not very beautiful, even ugly, I'm sorry. So let me see. We see a diagram X of shape J. In category C, we mean a functor of the form, why not call this F, J to C. So you could think of those as J or those as C. Okay. Then next I'm going to talk about what is called a cone. I'm not going to talk about this in general, I'm just talk about, so what I care about, we care about what is called a cone overall ender diagram. So let's say a cone over a diagram of type J is an object in C equipped with a morphism. Let's see, C equipped with morphism from small c to each vertex of F. Such that I haven't really defined what is vertex F. You could intuitively think of it as, so those vertex, whatever shape of diagram. As I said, I'm not defining this very formally, I'm just intuitively to quickly introduce to the exercise, such that every new triangle arising this way commutes. And under this, a cone, let me see, a cone which is universal is a limit. right? We know how to define limit and the colimit, but this is more intuitively because I can visualize it. It's not something fresh, new, but something make you feel things are better controlled. Let's say, let me draw a picture. So you have a diagram, let's say, and then a diagram, you see, right? And then you have a cone. As I said, a cone is again object in C, and then where you have epimorphism to all the vertices of F. So I'm just very abstractly, let me just symbolically write free arrow. There could be many, depends on how is your diagram. So, and then the universal one is basically right for whatever other cones it factorize through it. And for this way, you could think of it also as intuitively the closest cone is called the limit, right? The closest one. Or if you keep doing this in somewhere, they said the shadowest cone, because when you put down and then continue, you will see that this is darker and darker, and finally you got some darkest in the sense of color. While conversely, and again intuitively, you could think of a colimit as start with a diagram, right? You start with a diagram and then take the colimit. Colimit is, so each vertex of your diagram has an arrow to this element of C such that every formed triangle is commutes. And then it is universal, mean that for any other factorize it. Right, and then the closest one is the closest cone. Corresponds, or the universal corresponds to a colimit. Okay, very intuitively, of course, very quickly talking about those things. And then not yet finished. 6. What do I mean reflects? Reflect limits. So this video would be more like preparing for the next video, but I'm still going to do exercise at the end of this video. So a functor is said to be, or is said to reflect limits or colimits of given shape if a cone or a cocone, so this should be called a cocone, is a limit or respectively a colimit or maybe I should use adjective words, is limiting. Whenever its image under F is okay. So first exercise is epimorphism. Reflected. So actually I'm defining what you call reflect limits, which means if your image is, I think here is kind of vague. What do you mean by limiting, right? So we will see a more precise result. I mean, I'm not talking about this in whole generality. In whole generality, I'm just talking about particular case. So the exercise given will be very precise. I'm just saying that I'm going to talk about epimorphism reflected, which means if its image is epimorphism, then the starting morphism was epimorphic, then this is called reflected. And first exercise is saying that epimorphism are reflected by faithful functors. So this is very direct. Suppose you have a functor from F to D. Suppose you have two objects A and B and arrow F, and then I'm claiming that if after you apply F, your FA, FFB is epimorphism, then small f is epimorphism at the beginning, right? So if this is the picture, if FF is epimorphism, then by definition or by chapterization, this is the same as saying that FF, sorry, it's too early to talk about this. I'm going to prove this, claim this is epimorphism. If this is, right, okay, the proof is by equivalent chapterization of epimorphism, this is epimorphism is the same as saying that if you have any morphism from B to C, whatever object C, then F composed with J1 is the same as composed with J2 implies J1 equals J2. In the case that let me draw the picture, you have J1, J2, right? Which means you have right cancellation. And then I'm going to prove this, right? What I need is only this. It suffices to prove this. So I'm going to prove this. To prove this is to prove that this implies this under this condition. Okay, so now by our assumption, we have this, and then apply our faithful functor. This gives you FG1 compose FF equals FJ2 compose FF. And then the fact that FF is epimorphism, take implied that FJ1 equals fj2, and then this implies j1 equals j2 by the faithfulness, right? If you want to be more precise, this is because, so you have this two maps from B to C in the category C, and then this embeds into category D, FB to FC, while here you have fj1 minus fj2 this is 0, and so that is mapped to 0. I mean, yeah, if I'm talking about 0, I'm talking about additive category, or at least AB category. But without that, I'm saying that. So you have two maps, G1 and G2. They are mapped correspondingly to FG1 and FG2. The injective here means two different maps are mapped to different, which means if their images are the same, then the star shadow is the same, right? Okay, this is the proof. Exercise 2. So this is the main exercise for today. What I want to prove is that yes, here is the exercise 2. A fully faithful functor, for example, equivalently a full subcategory, category inclusion. Okay, I don't care about that. Let me just write a fully faithful functor f reflects or limits and colimits. Let's do the proof. So still under the picture, f is from C to D. And fully faithful. And let's say if you have a limit, if you have, so what I really want to say, that I'm using a very intuitively way. So you have this, so look at the case of limit. So you have a diagram, you have universal cone, right? And then you don't know, so actually you start with a cone and you don't know this is universal or not. And then you apply your f, and then you got f of this. So this is in C, this is in D. This again gives you a cone by a commutative diagram. Suppose you know that this is a universal cone now. Question is it at the beginning universal cone? So take any object at the beginning, so which is again a cone. Does this factor uniquely from this? So the answer is you just apply the functor f, and because this is a universal cone, it factor right through this. Right. Let me give a name to make it better understand. Let's say this is A and then this is B. So this is FA and this is FB. Right, so what is the situation? The situation is we look at home BA and home FB FA. So this is a bijection because this is a fully feasible functor. The question is, that there exists a functor from B to A, an arrow from B to A making all the diagram commutes, knowing that there exists a functor from FB to FA making all the diagram commutes already. Right. I mean, let's call this FF. Then there is this preimage of this, right? Let me call it F. So I'm putting this F here, and then I'm going to check. Check what? Check firstly, suppose there is the first diagram you are going to check. This is, let's say, this is some object C here. And so this map to F of C. Suppose you have a commutative diagram on this side, this right hand side, like this. Right, suppose you have this, and what you know at the beginning was that there was this and this, but you don't know there exists a map to make this commute or not. And now I put F here and question this commutative. So what you have is FF composed with FH equals FJ, right? Then by the fully feasible embedding. So here, this is both objects from FB to FC. But this is again a bijection with home from B to C. This is telling you you have, F compose H, compose F, which is the same as this. So you have two arrows. First is H compose F, second is G, and their image are the same, implies they are the same at the beginning of this bijection. So this finishes the proof. Okay. So this would be used. So let me put application or remark. For example, you have the category and then this H of let me call it H of C. You need the embedding. This is fully feasible, and in particular this reflects limits and colimits. So I only proved for limits. You could complete the proof for colimit by yourself. And also because this is fully feasible, some exercise. Let me think. This also preserves So preserves limits. So preserves limits,